Hi, I'm Kristen Howell. I'm a manager of data science and machine learning at LivePerson. And today I'll be talking about typologically grounded grammar inference. This work was done while I was at the University of Washington with collaborators in the Aggregation Project, Emily Bender, Faye Shaw, Olga Zamarayeva, and many, many others. The primary research question that I'll be exploring today is how and to what extent can we generate linguistically rich grammars for typologically diverse local languages? And here I'm using the term local as defined by Bird 2022 to describe small, primarily oral languages, often indigenous or endangered, and including the original and emerging languages of Africa, Asia, Australia, the Americas, the Pacific, as well as the minority languages of Europe. In NLP, these are often referred to as low resource languages, but this framing seeks to shift focus away from the Western NLP resources that we tend to focus on and onto the types of resources that these languages do have. And as you'll see later in the talk that even though we're working with rather small corpora in terms of how many sentences they might include, these are actually very rich corpora. So the outline of this talk will be as follows. I'll talk a bit about precision grammars. These are formal linguistic grammars and what they're useful for. Next, I'll talk about automatic grammar generation and how this ranges from inferring or generating very simple grammars all the way to formal linguistic grammars. And then I'll talk a bit about grammar inference with a system called BASIL, which we developed as part of the Aggregation Project. So precision grammars are machine-readable grammars. They're collections of syntactic rules, and in this case, those rules will be encoded in the Delphin joint reference formalism, although in principle, any formalism could be used. These collections of rules that constitute a grammar can be loaded into software to parse sentences. Once the grammar is loaded, parsed sentences will generate an output, and that output will take the form of a syntactic and/or a semantic representation. Again, in this case, the syntactic representations will be in the head-driven phrase structure grammar formalism of syntax, and semantics will be using minimal recursion semantics. That said, again, any formalisms could be used in principle. Now, once a semantic representation has been generated, that representation can be used to generate more strings in the language that meet that meaning representation. So these are bidirectional grammars. To give a little more concreteness to this, here's an example of a syntactic rule. It's not necessary for the purposes of this talk to understand everything going on in this syntactic rule, but I'll draw your attention to a couple of things to illustrate what's going on here. So first of all, this is a lexical rule, and it selects as its daughter something with the head verb. So that means this is a lexical rule that applies to verbs. It also adds a negation relation to the list of predications. So the semantics are going to include this negation relation. This is a rule for adding sentential negation. So as you can see, those negation semantics are added to a verb. This is a suffix, and as you'll see here, right, that suffix corresponds with a particular orthography. So when that orthography is seen in a string of words, if the inputs match the appropriate verb class, for example, then this rule can be triggered. So a grammar is made up of many, many rules of this type. And once loaded into parsing software, that grammar can be used to parse sentences. Throughout this talk, I'm going to use a running example from the language Sintang, which is a Sino-Tibetan language spoken in Nepal. I took this sentence from a corpus that was developed by the Sintang language research program. And this has been a very long-standing language documentation effort. So this corpus is extremely large, extremely thorough in its glossing and segmentation, and is an example of the type of data that is generated by documentary linguists. So this sentence, which translates to English roughly as "they did not know another language," can be parsed as follows. So first, the root will go through a number of lexical rules to get all the appropriate prefixes and suffixes. And then that verb will go through a comp-head rule, which allows it to take its complement, which in this case is another. And once taken its complement, it goes through a head-opt-subj rule to drop the subject because the subject is not overt in this sentence. This syntactic representation maps to a semantic representation, which can be represented as a dependency MRS. So here in this dependency representation, we see different arguments and their dependency relationships. We also get a predicate argument structure. So the verb know is a proposition in this case. It has a tense non-past, an aspect, and then its first argument is the subject. So that is third person non-singular number. And its second argument is the object, which is third person. So as you can see, these parses, these representations are extremely rich from a linguistic perspective. So that's what a precision grammar is. Let's talk a little bit about what they are useful for. So one use of precision grammars is tree banking. As you likely know, the process of developing a tree bank is very time consuming, especially if drawing trees by hand. However, if you have a precision grammar, then even if you want, your tree bank to be in a very detailed formalism, generating those trees is very, very quick. And then the only manual effort comes from going through and accepting correct parses and rejecting incorrect parses. This is also incredibly useful for discovering ambiguity. So computers are really, really good at finding every possible meaning, even when humans struggle to do this because certain readings, which are perfectly grammatical, are pragmatically odd. So for developing a very robust tree bank with lots of different possible representations, a grammar is very helpful. These grammars are also helpful for data exploration. So the question you might be asking here would be, what occurs in my data? What occurs in my language? So if you wanted to find examples of sentential negation in your corpus to see how it occurs and find examples of sentences for illustration, then you could use a precision grammar to do that as well. These grammars have also been used for developing educational resources, such as grammar checkers or automatic tutors. Now, the grammars necessary to do this are very well built out. They cover lots and lots of phenomena. And as you'll see in this talk, the grammars that we're generating automatically are much smaller. So as it stands now, an inferred precision grammar using the BASIL system would not be useful for developing a grammar checker or automatic tutor. However, we do see this as a very important area of future work because especially in the context of local languages, often these languages might be endangered and have an ongoing revitalization effort. So technology like this can be very useful. So if precision grammars are so great, why don't we see more of them? And the main reason, in my opinion, is that they are incredibly time consuming to write by hand. So the field of grammar engineering involves developing syntactic analyses, implementing them, developing out grammars, and then testing sentences, looking at interacting phenomenon and making sure your analyses for those phenomena work. This is really a much larger skill set than syntactic analysis by itself. It's also a different skill set that might be used in language documentation. And so it's a big ask from linguists to also do grammar engineering. And as a result, grammar engineering toolkits have been developed to streamline this work. So in HPSG, we have the grammar matrix and CoreGram. In LFG, there's a toolkit called Pargram. And what these toolkits do is they store analyses that are cross-linguistically useful or that can be customized cross-linguistically. And enable those to be used as a starting point for developing a grammar. Still, after this point, the grammar must be built out further by hand. So to make this more concrete, I'll take you through an example of how the grammar matrix customization system works. So the grammar matrix customization system uses a web-based questionnaire to elicit information about the language. So the linguist or grammarian would answer questions like, if we're modeling sentential negation, what's the morphosyntactic exponents of the negation construction that you'd like to model? In other words, is there a single morpheme like not in English, or two morphemes like ne pas in French? And given the number of morphemes that are necessary, are these morphemes or morpheme free or bound? So do we have an affix, or are we looking at independent words? And the answers to these questions will be encoded in a grammar specification. This grammar specification looks something like this for negation. And so here's an example again from Syntong. The exponents of negation in this language is 1. And the negation morpheme can actually be either bound or it can be a negation auxiliary. The bound morpheme is represented with this orthography in this lexical rule that has a negation feature on the verb. This rule, this specification will then be transformed by the grammar matrix into this lexical rule, and that rule will be one of many in the output grammar. So the grammar matrix currently handles a large range of phenomena, and so you would go through and answer the questions for a nominal possession, word order, case system, case frame. You'll specify a lexicon. There's also categories for valence change, WH questions, etc. So even answering that questionnaire, especially in the case of specifying the lexicon and the morphological rules, is still quite time-consuming. So our question here is, can we automate more of this process? And that's what we seek to do in the aggregation project, and that brings us to automatic grammar generation. Now, the field of automatic grammar generation has been around for a long time, and began with grammar induction from strings. So, or not began with, but one of the early types was grammar induction from strings. And so what this sought to do was use text alone, and based on just that input, generate a grammar. As you can imagine, these representations were noisy and only partially aligned with the trees that are created by linguists. Some early work did this by identifying constituents and identifying their categories, and then building out syntactic rules from there. More recent work has used neural nets, and so there was some work by Hewitt and Manning a few years ago that used BERT to generate parse trees. Now, this did not produce a human-readable grammar per se, but it did generate a parser that could produce trees. There's also been recent work that pairs text alone with an image. So, for example, using captions and images together. And this has been found to improve recall and improve the identity of the syntactic categories. However, these representations are still quite noisy and rather impoverished. So another field has used strings paired with meaning representations. And so in this case, we'll have in the input text together with some semantic representation, either a logical form or a semantic dependency parse. And the result will be a grammar that can produce semantic representations that are similar to those that were included in the input. Now, grammar extraction enables us to produce more formal grammars. Basically, whatever type of parse tree or semantic representation that's in the input, the generated grammar will have roughly the same level of expressivity. So a common way to do this early on was to walk the trees in the tree bank, collect the rules, and then prune any unnecessary rules or redundant rules. There's also been some work that converts from one formalism to another. So in the case of Shaw or Hockenmayer and Steedman, the Penn tree bank trees were used in the input, and then they converted the representations to CCG or something like that. So you can get really rich trees using this, but again, you are somewhat limited to the level of expressivity that was in the input. Now, more recently, the Kermit system used BERT to generate syntactic parses based on syntactic trees that were included in the training data. So again, we had trees of a similar form in the output as in the input. And again, like with Hewitt and Manning, a human-readable grammar was not generated, but instead a parser was. So finally, we have grammar inference. And grammar inference is different from grammar extraction in that it doesn't require a tree bank, but different from grammar induction in that it does allow us to generate formal linguistic grammars. And the way this is done is by pairing a text that is annotated with partial grammatical information with some external source of linguistic knowledge. So work by Bender and Helen and others have used interlinear gloss text data. This is linguistic data that I'll show you an example shortly, but that has morpheme segmentation and then glosses that include information about morphosyntactic features, and then there's an English translation as well. Other work, used a custom format that include POS information, predicate argument structure, clause type, and things like that. And then this external source of linguistic knowledge could be anything from a grammar engineering toolkit, like in the case of the grammar matrix, or for work that was inferring minimalist grammars, a collection of minimalist axioms and a concept of merge. So where does typology fit into all of this? In the case of grammar inference, we're using an external source of linguistic knowledge, and that source of linguistic knowledge needs to be cross-linguistically robust. So in the case of the grammar matrix, which we use in the aggregation project, the grammar matrix was developed by first surveying the typological literature and then developing analyses in the customization system to account for this typological range. It's also useful along the way for producing grammar specifications to infer typological features. And finally, any inference system that we want to be cross-linguistically generalizable needs to be developed with typological diversity in mind. And so you'll see later in this work, we use a broad range of typologically diverse languages during development and evaluation. So let's talk a bit about the aggregation project and grammar inference with BASIL. So the aggregation project has had a number of contributors throughout the years, whom I've listed here. And the goal of this project is to bring the advantages of precision grammars to documentary linguists without the documentary linguists having to do the effort of grammar engineering themselves. So we have an aggregation pipeline here. And the goal is to start with a corpus of data used and developed by documentary linguists and to end with a grammar. So the input corpus will typically be in the Flex or Toolbox format, as these are the most commonly used by documentary linguists. Although we've also done some work using descriptive grammar books, as well as collections of IGT scraped from academic papers. This data is then converted to the SIGTYP data type. This is an extensible and flexible XML-based format. And that SIGTYP corpus can be input to a system called intent. Intent enriches or adds to the IGT data by projecting English dependency information and part of speech tags onto the language. That enriched corpus is in the input to BASIL and the MOM morphological inference system. And together, these two systems output a grammar specification. That grammar specification can then be taken as input by the grammar matrix, which will in turn produce a machine-readable grammar. That machine-readable grammar can be loaded into software for parsing or tree banking. So grammar inference with BASIL covers a number of phenomena, including lexical, morphological, syntactic, and syntactico-semantic. The work of lexical and morphological inference is done primarily using the morphotactic inference system. So this system does the heavy lifting in terms of developing lexical classes and morphological rules for intransitive and transitive verbs, as well as common nouns. The BASIL inference system also identifies auxiliaries and differentiates those from the other verbs in the corpus, differentiates pronouns from common nouns, and then it does additional inference for other lexical types, including determiners, coordinating conjunctions, negation words, and case marking adpositions. On the syntactic side, BASIL provides inference building on previous work for word order and case system and case frame, and also includes new inference for argument optionality and argument marking on verbs, sentential negation, and coordination. It also infers syntactico-semantic features, including person, number of gender, and tense aspect and mood. This here is still only a subset of the phenomena that are modeled by the grammar matrix. So there is room still to expand on this within the limits of the grammar matrix to handle more phenomena. So one important area of research that we've done has been looking into mapping features from WALS, because as you can imagine, a lot of the information we need to generate these grammars, like word order, is already available in the WALS catalog for many languages. Now, the WALS feature database is somewhat sparse, but there have been efforts, including the SIGTYP 2020 shared task, that make a huge step towards increasing the available information for languages and features in the database. So previous work by Dalmadia et al. Found about 20 WALS features that could be directly mapped onto grammar matrix features. Now, this only accounts for 8.5% of the grammar matrix's specifications, but preliminary work, which incorporated WALS features into inference, did show that this is still useful, even though you need to infer more information along the way to model the type of negation, the type of coordination. Knowing the overarching typological features provides a useful sanity check during the inference process. So the grammar inference done by BASIL is largely heuristic. It leverages linguistic annotations in the forms of morpheme segmentation, POS tags, and morphosyntactic features, and also leverages enriched IGT data. So as an example, up here we have a sentence in IGT format. So we have morpheme segmentation on the language line here. And then we have glosses below. So, this gloss shows us third person non-singular subject agent, the verb meaning the root no, and then third person agreement, indicative aspect, non-past tense, and negation. So this is very rich by itself. And then the intent enrichment system from Georgie 2016 takes us a step further by parsing the English translation to identify these dependency tags and POS tags for the English sentence, and then doing alignment between the language line and the translation line via the gloss line. So for example, in this case, the another and another happen to be the same word, but some more sophisticated methods are used if we don't have an exact string match here. But this allows us to identify that these two correspond to roughly the same verb, and then the dependencies through these alignments can be projected onto the language line, as can the part of speech tags. Now, this isn't a perfect system, right? We don't have one-to-one mapping of word categories, much less dependency relationships from language to language. But it does provide us with a very useful starting point for inference. So how might we generate a grammar specification using this enriched IGT data? So here's an example, again, of negation, where we take this IGT and we infer sentential negation. So this example of sentential negation shows us a single negation morpheme. So we know our exponents is 1. We know that inflectional negation is one option. And then other sentences in the corpus would tell us that negation by auxiliary is another option. And then we also infer this lexical class. Again, the morphological inference system will break us down into lexical classes and then position classes for the morphology, and then add this negation feature to the verb. So we do this inference for, again, a number of different phenomena, and that outputs an inferred grammar. That grammar can then parse a sentence, like the representation we saw previously, right, where this inferred lexical rule allows us to generate these syntactic and semantic representations. So during development of the BASIL inference system, we used a total of 27 languages, 9 of which were core development languages, shown on the map here in red. These development corpora, we worked with very closely and did iterative development. So, we would model one phenomenon, we would test it on the corpus, and then model the next phenomenon and see how that affects our coverage. These corpora are primarily toolbox and flex data. Again, that's the format used by most documentary linguists. But we also used a grammar of Wambaya from a book, Descriptive Grammar, which shows us that we can use this if we wanted to, for example, generate grammars to accompany descriptive resources. So we had a total of 9 development languages, and then because even though these are great examples of the format that linguists use, they don't cover that many language families. And so we consulted an additional 18 in order to supplement our research. And so these consulted languages would help us to model a specific phenomenon that we wanted to make sure we had data to test. And then finally, we evaluated on held out data from 5 language families that were not in our core development languages. And this allowed us to test the cross-linguistic generalizability of our system. So the development corpora, sorry about that, I had a duplicate slide. So the iterative evaluation on development languages allowed us to go through and see how our coverage improved as we added more phenomena, and also to test the interactions of the inference. So it's noteworthy here that even in our best case, our lexical coverage for a buoy was just over 50%. Now, this makes sense when you consider that we handle transitive and intransitive verbs, but not clausal complement taking verbs, for example. We don't handle adjectives at this stage, and we don't handle a nominal possession, so any possessive pronouns won't parse. So what's more important to look at is what is the parse coverage within the lexical coverage? In other words, of the sentences where we have an analysis for every word in that sentence, how many of those sentences parse? So here we find, it ranges still from, 50% to, closer to 80%. And in this case, still, we'll see, for example, we don't handle yes, no questions. So even though an additional word isn't necessary for this, a syntactic analysis is. So that parse coverage still doesn't quite span the lexical coverage. We also did tree banking to identify how many of these parses were correct in terms of the correct predicate argument structure, and also having the correct predicate argument structure and semantic features, right, like person, number, gender, etc. So, so you see here that, you know, it is possible in some cases to still not have correct parses, even on development languages that we worked with really closely. So we tested the generalizability of this onto 5 held out languages. And those held out languages came from language families that were not represented in our development languages. These ranged in terms of the size of the corpus. So our smallest was this corpus of WALS, which only had, 683 sentences in it. This corpus was developed actually during a language documentation course. So it's quite small. The sentences that are included cover very targeted phenomena. And as a result, we see our best coverage for that language. Others were much larger. This corpus of Arapaho, for example, was much larger than 5,000 IGT. And we just sampled down to 5,000 to have a more reasonable number. And this corpus included a lot of transcribed speech, which included disfluencies in the IGT itself. And as our inference system doesn't handle disfluencies, our coverage for Arapaho was very, very low. In between, those extremes, the South Efate and Teton had, relatively lower coverage. But again, what's important here is to look at the parse coverage within the lexical coverage, and then the correct predicate argument structure and features within that. So these results may not look impressive by themselves, right? We're still, we have lexical coverage over less than 40%. Our correct coverage is closer to 5% for most of the languages, except for WALS. So we compared this with some baselines for how might we do this inference if we didn't have this external source of linguistic information. If we could only infer a lexicon using the morphological inference system, and then just input the syntactic information in a naive way. So we used a random baseline where the typological features were selected at random. We used another where we selected the typologically most common analysis. So to make this concrete with an example of word order, for the random baseline, we'd select a word order at random. For the typological baseline, we would choose the most common word order in the world's languages. And then a broad coverage baseline allowed us to pick the one that was expected to give us the most parses. And so in this case, we would select free word order, which will parse anything correctly, but then also overgenerate. And comparing the BASIL inference system with the broad coverage grammar, which we expect to do the best, we do see pretty similar coverage in terms of lexical and parse coverage, but the correct coverage is generally lower, with the exception of cases where the broad coverage grammar, where it couldn't necessarily guess morphotactic features, but if sentences didn't have any morphotactic features, then getting the correct structure was fairly easy for that baseline. So for the past 4 years, we've been using, or Emily Bender has been using, this inference system in a grammar engineering class. So this is a graduate level course at the University of Washington. And historically, over the course of the class, students will get as much out of the grammar customization system as possible, answering different questions in the questionnaire to get a starter grammar, and then build out that grammar by hand. Using the BASIL inference system, they've gotten a much more robust starting point. So they'll have a number of the correct analyses in their grammar right from the get-go, and then simply need to refine that by hand. This is one of the big helps from this, is that it gives parse coverage from the start. And that allows them to find illustrative examples from the corpora that they're working with. So because they can find examples more quickly, then they can, instead of developing examples by hand, they have real data to work with. It also allows them to use bigger lexicons and actually leverage a corpora to work with. So instead of having to create small test suites that use the same handful of nouns and verbs, they automatically get this lexicon and can use real examples from the language at a much broader scale. Doing this also saves time. So instead of answering the entire customization system by hand, they get this jumpstart. They can get more out of the customization system and then move to modifying the grammar and building it out beyond that. One of the downsides to using this has actually been that it's very tedious to correct the inferred morphology. And so that's an important area for future work, is to refine the morphological inference so that it's a bit more robust and doesn't need as much refinement. There is ongoing work along these lines. Actually last year, Conrad's thesis reduced the ambiguity in the inferred grammars. And then there are a couple of master's theses in progress to improve root detection in the morphological inference system, as well as adding new inference for nominal possession and for valence changing morphology. And then finally, there's a student now working on processing more data so that we have more corpora to work with, and we can find more phenomena to model from these corpora. And also he's fixing matrix bugs, and since any bugs in the matrix system impact the effectiveness of grammar inference, this is incredibly useful. So just to conclude, we've talked about precision grammars today, and that they're useful for a number of things, including tree banking, data exploration, and language learning. But they're very difficult to build. So the BASIL grammar inference system leverages typological information, typological knowledge to generate grammars automatically. While these grammars are small and their coverage is still somewhat limited, the parsers they produce are incredibly rich linguistically. I want to thank you for listening to my talk. It's been a pleasure, and I also want to give a thank you to all of the former and current contributors to the aggregation project, those on whom this work built, as well as those who are building that out further. We're also deeply indebted to the speaker communities who provided linguistic data for documentation, as well as the field linguists who shared that data with us. And finally, this material was funded by the National Science Foundation. Thank you.